So hello everybody. Today we will discuss about auto transformers. So till now we have discussed about two winding transformers, basically single phase transformers, where we have talked about different aspects of it. The voltage regulation, efficiency, equivalent circuit diagram of it. So all these things we have discussed for two winding transformer. Okay. Now we will discuss about auto transformers. So in some cases what happens is, let's say the generator and the load are far away at a very long distance. Okay, and because of this there is a drop in the transmission line, and obviously that drop is because of the transmission line impedances. Since this drop is not so much, so what we want is to maintain that voltage level in middle of of that transmission line somewhere. Now there are two ways of doing it. Either again we need to put let's say the two winding transformer. Let's say if it is a 3-wire system, then obviously 3-phase transformers there. Then what will happen there is, let's say if primary side voltage is at, or let's say for long transmission line, generally the let's say for long transmission line, generally the voltage level is around, let's say 400 kV. Now that voltage level, because of the long distance and voltage drop in the transmission line, that voltage level has come down to a level of let's say 395 kV. Now we want to step up this voltage. So if I design a transformer for it, let's say two winding transformer, the transformer based on two winding transformer principle, where primary is separate and secondary is separate, then in that case we would be needing the full voltage windings, right? Let's say a transformer whose voltage, whose turn ratio is meant for primary side, meant for let's say 398 kV, and the secondary side around 400 or 405 kV, let's say. But obviously then this will take a lot of copper in the windings, and even the transformer size would be as huge as the main transformers there. So the other way of doing it is using an auto transformer. So in an auto transformer, basically it's not a two winding transformer. So in a two winding transformer, primary and secondary, they are separate. But in auto transformers, we tap the secondary out of the primary. This auto transformer can be step down or step up transformers. So generally, if you'll see the circuit diagram of it, it would be like this. So this is a step down auto transformer. I am showing it for a single phase. This can equally be made for the 3-phase as well. Step down auto transformer. For auto transformer, I would be using A/T. Okay. So this is the primary side, and at the secondary you are actually tapping the load, you are connecting the load here at the secondary of it. Okay. And similarly the reverse is also possible, that you can step up the voltage as well, and this is step up auto transformer. So today we will discuss about its working principle, how the MMF is balanced, and then we will talk about its kVA rating, and then we will talk about the equivalent circuit diagram of this auto transformer in a practical sense. Okay, so this is step up auto transformer. So the one advantage of doing it is, let's say this is 395 kV, and then I have to design only for 5 kV here, right? And this will give me, as I was discussing before, that let's say this side 395 kV voltage is coming, and at this side I would be getting, like I need to design it with like the extra number of turns which would be required would be only for 5 kV. Okay, so actually this is helping me in saving the number of turns. If the same case, if I would have solving this problem using a two winding transformer, then I would have used a copper winding here. We should be able to handle 395 kV here, and another, the secondary of it, with 400 kV. Okay, obviously in this second case, in this two winding case, I would be needing a copper which is equivalent to this amount of voltage, right? This amount of number of turns. So this would be a little costly affair. Obviously, the thickness of it, then we have to decide what would be the thickness of the copper here, and thickness of the copper here would be different. Okay, and if I'm using this, obviously obviously here the thickness of this copper wire would be different, right? So that it handles the current which is actually passing here. Okay, so this is the reason why we need to study about auto transformer cell, because it is used in the power system. And then for small applications also, like in our lab where we vary the AC voltage, we use these kind of auto transformer cells. Okay, so what is the working principle? So if we see the working principle, I'm just showing the simple diagram actually. So in practical sense, if you'll see, actually we have the winding done here. Like in two winding, we have two windings on the limbs, but in auto transformer, basically it is on, we have the winding on one limb only. Okay, or I won't say that on one limb, rather this entire core, either in circular one or a desired shape, we can actually wound on this entire core, a single winding on this entire core. Okay, the number of turns. So this actually helps us in saving the copper, in saving the core material as well. Okay, so for the simplicity, I'm showing just on one limb. So if you'll see that, obviously if we energize it by a AC source, so because of the Faraday's law, we'll see that we will have the induced EMF here as well. And let's say the dot for this is here. That means if I'm increasing the current in this direction, the induced EMF will have this polarity. The positive would be in this direction. Okay. So this secondary is actually tabbed somewhere from here, and from here, and we actually connect the load here on the secondary. So obviously, let's say if the load has been connected, okay, and this switch has been turned on. So before turning on the switch, what will happen is this core will get magnetized because of the excitation which has been connected across these two terminals, across the primary of it. Okay, so and because of this, the core will get magnetized. And let's say for us right now, I'm assuming that the permeability is infinite. Okay, so very good material, very good magnetic material. So obviously the reluctance is 0 then. Okay, since the reluctance is 0, so it won't require any magnetizer current, and the moment I have energized it, the core will get magnetized, and let's say desired amount of, depending upon the voltage, the desired amount of flux will start flowing into it here. And obviously the induced EMF, if you will see on the primary of it, let's say this entire number of turn is N1 here, so this E1 would be 4.44 F phi m N1. Okay, let's say the tapping which I have done here, the amount of number of turns here is N2. So N2 is between these 2 points, and N1 is this entire one. Okay, so induced EMF, even if I say E1 is across this entire coil, so that is E1 is this much. So the moment, obviously we know the induced EMF or the per unit, the induced EMF per unit number of turns, if you see that they would be same, right? E1 upon N1 would be 4.44 F phi M N1. So depending upon our requirement, I will decide what would be the number N2 here. Okay. So obviously, the moment I said the number of turn is N2, so according to number of turns, there would be induced EMF there. Let's say that induced EMF is E2 then. Okay. Then E2 would be given by N2. E2 by N2 would be also be the same, because the same flux is being linked with this number of turns N2. Okay. So here actually this would be N1 I have taken here. So same flux would also be there, right? So E2, if you'll see, would be 4.44 F phi M N2. Okay. So if I say this E1 by E2, that would also be equal to N1 by N2. Okay. Now, the moment you have connected this switch, you have turned on this switch, so obviously this will draw some current depending upon the load impedance and the voltage there. The equivalent amount of current will be drawn from this circuit. Okay. So let's say that amount of current is I2 here. Okay. So this I2 will actually draw the current from the source, right? From the source as well, right? So this current, let's say, is I1 here. Now you see this. What would be the direction of I1 based on this winding? The direction of I1 is here, right? These are all direction of I1. And here the current will actually get divided, right? So at this junction or at this node, we would be having the the sum of the current, because this I2 would be actually fed by the current from this voltage source as well, E2 as well, right? And some current is actually being drawn from this source, V1. Okay. So let's say I1 is flowing in this direction. It is started from here, an entire coil, and then it come out from here. So this is I1. So here we have I1. What about I2? So if we see the direction of I2, this will actually push the current in this direction. Here, this is I2. Right? And then I2 will come out from here. This is I2. Okay. So in this branch, what we can say is, in this branch, if we see the nodal analysis at this node as well. So at this node, this would be, let's say, I1, and I2 is going in this direction. Let's say this current in this direction is, let's say, Ix. So it would be I2 minus I1 would be the current in this branch, Ix. Okay, in this branch, the net current here. So see, I said, and you can think of in terms of dot convention as well, because if dot is here, let's say for winding 1 dot is here, obviously for winding 2 dot would be here only, right? Okay. So for winding 1, if dot is here, for winding 2 also the dot is here only. Then only the voltage will get added up, right? If winding 1 dot is here, the other for this one, the dot should be here. Then only you can add these voltages, right? We have seen in the dot connection, the lecture on the dot connections. Okay. And in the dot connection, what we have seen that if current enters in the dot, then from other dot, the current should leave, right? So from the dot, the current is going in this direction, right? Current is towards the winding or towards the core, the current is actually leaving, right? So because of the second dot, I would say the current should actually enter from the winding towards this dot, right? And then only if you see, now if you see the flux, the direction of the flux. So direction of the flux, because of I1, if you'll see, it would be in this direction. right? It would be in this direction, right? But what would be the direction of flux because of the secondary current or because of this I2? If you see, because of this I2, the current, the direction of the flux, you see here, so the direction of the flux would be opposite to it. Okay, it would be opposite to it. Okay, and that's how the net MMF or net flux in the machine will remain constant. Even if you load it, equivalent amount of current would be drawn from the source and net MMF would be balanced. So net MMF would be balanced here. So if I draw the equivalent, the MMF circuit of it, for the above one, obviously if N1 is the entire number of turns and N2 is for the lower portion, then for this portion we have N1 minus N2 number of turns, right? This N1 is entire one and N2 is for the lower one. Then for the leftover portion it would be N1 minus N2. Okay, so if I draw the MMF now, so MMF, let's say for plus here and minus here, and this is N1 minus N2 number of turns into I1. Okay, and here if you'll see, the flux is in the opposite direction, so minus here and then plus here, and this would be N2 into I2 minus I1. And since no reluctance, I am showing it here. Okay, that means the MMF, net MMF would be almost zero or equivalent to the amount of magnetizing current. And since we have assumed that reluctance is zero, so magnetizing current would almost be zero. So what we can say is net MMF is zero. So N1 minus N2 into I1 is actually equal to N2 into I2 minus I1. Okay, so let's try to solve it. So N1 I1 minus N2 I1 is N2 I2 minus N2 I1. So this and this gets cancelled and we have again the same expression as that of two winding transformer, right? So N1 I1 is equal to N2 I2. This implies we have I1 by I2 is equal to N2 by N1. And if you see the apparent power rating of the primary side and the secondary side, that would be V1 I1 upon V2 I2 would be equal to 1 here. So that means apparent power of both the side is also same. Here the apparent power of primary side and the secondary side is same. Okay.